Okay, so looking at the reactions of the alcohols then, there's three types, and I'm only going to look at the first two in this one. The first one is combustion, which I'd expect really all of you to be able to do. The only thing you need to take into account if I do go through this one, so two carbons, so two carbon dioxides, there's 6 hydrogens, which means you're going to have 3 waters. The key thing from here is working out the oxygens from that, because over here now I've got 2 2s are 4, 2 2s are 4 oxygens there, plus 3 over here, which makes 7. However, there's one of them in the alcohol, so you've got to take that into account. So take 1 off the 7, which leaves you with 6, which means you've got to aim to make 6, so you need 3 lots of oxygens there. Okay, so they should be fairly straightforward. If you remember in the last one, we looked at one of the ways that we can make alcohols is by using alkenes. It is actually a reversible reaction. So the second one we're going to look at is the dehydration of an alcohol. Now, dehydration means losing water, which basically means that your alcohol is going to lose an OH on one carbon and a hydrogen on another carbon. Okay, and it has to be adjacent to where the OH is, or next door. So where you remove the water, the OH and the H, is where the double bond is going to form. So that will form there, which gives us our final product over here. In terms of the mechanism, so again, we're using sulfuric acid, so an acid as a catalyst. So, and just again to remember, sulfuric acid will also dissociate to give you 2H plus SO4 2 minus, and these are that bit there. Remember the oxygen is D minus, the hydrogen is positive, so they're going to be attracted to each other. The hydrogen ion can accept a pair of electrons, and the oxygen has a pair to donate. So there's our first curly arrow there. At this point, we've got to eliminate water, and I hope you can see that this is the water that's got to be eliminated, and it's already lost one of its lone pairs, so the curly arrow is going to go back onto that oxygen to give you the water that we've got over here. Now, to put the double bond back in, we need to remove a hydrogen, again, next door to where the OH was. So remember, the OH is here on this carbon here, which is this carbon here. Next door to that is this one. So this hydrogen here will be lost. And in order to regenerate the hydrogen ion, the pair of electrons have to go in between these 2 carbons here and here. Okay, so our double bond, if I can just rub a few bits out there, the double bond is going to form at this position here, okay? And it's these electrons that are going to that point there that are forming that double bond, okay? So that's all fairly straightforward, so long as you've got an alkene that is symmetrical. An alcohol that is symmetrical. The moment you have an alcohol that is unsymmetrical, you can get 2 different types of alkenes formed. Remember what happens. The OH is taken off, so there's the OH there, and it takes with it, to make the water, a hydrogen on an adjacent carbon. Well, that's the carbon that the OH is on, which means the adjacent ones, which I'll do in blue, is here and also there. If I can get that coming there. There we go, and the blue one there. Okay, so what that means is there's 2 possible positions where the carbon-carbon double bond can go. It could go in this position here, or it could go in this position here. If it goes in this position here, it's going to form that alkene there. And if it goes in this position here, it's going to form this alkene down there, according to the mechanism that we've just gone through. The thing to watch out for here is once you've made your two alcohols, so we've got this alcohol being made and we've got this alcohol being made, this second one, this one here that I'm just putting a star in, that one can also give you EZ isomerism, which basically means, and the exam board are really sneaky with this because they often ask you to draw the three structures when you dehydrate an unsymmetrical alcohol. So one of them will be that. The second one would be the E isomer, and the third one would be the Z isomer of this alkene down here. And this is where all these definitions come in. If you remember, it only exhibits EZ isomerism if you've got two different groups on each side, on each carbon in the carbon-carbon double bond. So there's one group, there's a second group that is different. And on the other one, again, I've got one group here, one group there. That's two different groups. The one above doesn't exhibit EZ isomerism because I've got two groups that are the same on that carbon there, okay? So when you've got two different groups on each carbon of the carbon-carbon double bond, it will give you EZ isomerism, okay? And again, there'll be a few questions for you to have a look at there. And again, I think that's probably a good point to stop at here.